Hello everyone, my name is Carlos Pazos, and I will be presenting our work, XSnare, Application-Specific Client-Side Cross-Site Scripting Protection. So let's start off with what is cross-site scripting, also known as XSS. Well, let's look at an example from a WordPress website running the responsive cookie consent plugin. So in this case, let's say Bob is an admin of the site, and on the admin page, there's a text box expecting some numerical value as input. And so in a normal use case, Bob might input a value 0. On the HTML, this will reflect it as the input element having the value attribute set to 0. And all of this information is stored server-side. So whenever another admin of the site loads to the exact same page, the value of 0 will automatically be displayed to them. Now, in this particular case, the server-side does not perform any validation from the client-side input. So another admin, Alice, wants to exploit the weakness in the server-side code. What she'll do is she'll try to craft this special string that tries to close the input element early and inserts a script that redirects the browser, the page, to another malicious site. So on the HTML, this will be reflected as the input element now being closed early after the value attribute, and there will be instead a script element right after, which redirects the site to this malicious site. So when Bob loads this page, what happens is that his browser is immediately redirected to the malicious site. Now, XSS has been in existence for as long as the web has existed, but it's still a big issue. Almost 90% of the websites are still vulnerable to XSS attacks, and 14% of all web attacks are comprised by XSS attacks. From an example in 2018, card data for 380,000 visitors of the British Airways web application was stolen, and the company itself may be on the receiving end of a fine of up to 500 million GBP. In many cases, users are helpless against these XSS attacks. So first, we know that users need the web. Users need to be able to buy their tickets. Users need to be able to look at their email, and users need to be able to look at their calendar. And yes, all of these applications have been vulnerable to XSS in the past. This becomes even worse when we know that the stack is working against users. So the average time to fix an application vulnerability is about 38 days. And almost a third of the Alexa top 1 million WordPress websites are still running vulnerable software. So even if application developers fix their code, web page admins have to update their sites to run the last version of the code. There are some solutions that give users some agency, and because they're done on the client side. However, even these solutions suffer from some issues. For example, NoScript, which is an extension that disables JavaScript on a whitelisting mechanism, might disable usability because in cases where the web page is not well known by the user, it won't let the user run JavaScript. Similarly, the Chromium XSS Auditor, which is an XSS filter, is a bit too generic and doesn't really get rid of many exploits and was actually deprecated for this exact same reason. So solutions do exist, but in many cases they require server-side changes, and the developers might not have their time or their resources to keep up with user demands. They might also need browser modifications, and users might not be willing to adopt and install new browsers. They might have all or nothing approaches, which greatly impact usability. And finally, they might also have generic detection mechanisms, which help in many cases, but in the more special handcrafted ones, they won't be able to do much. So users are often left at the mercy of the developers. And so we ask ourselves this question: can we precisely defend against XSS on the client side? Our solution to this is XSnare. So we know that websites often give enough context to determine if an element belongs in a specific place of the site. So given some previous knowledge of the web app content, we can tell if an XSS vulnerability can occur. Our idea is to use signatures to prevent malicious code at specific points in the document, and we can enforce these signatures by a browser extension that runs on any loaded page in the browser. This allows users to defend themselves. Let's look at an overview of our approach. Let's say a user is running our extension in their browser and they want to load facebook.com. And before this, a security analyst has uploaded a signature to a database that specifies that facebook.com might have some malicious content. The extension that loads the signature and when it's processing the request, it detects some malicious content in the HTML document. And according to the signature, it sanitizes it and deletes this malicious content and passes it on to the DOM rendering for the user to browse the clean document. Some of the main requirements for our system are, first, that we need to be able to isolate injection points effectively. Second, we have to have an effective signature language to cover a wide variety of exploits. And third, we have to apply signatures to the correct pages. We don't want to apply signatures to pages that they don't correspond to, and vice versa. Finally, we have to be able to sanitize pages properly, because we don't want to sanitize too little or too much. For isolating injection points, let's go back to our example. In this case, we know that the injection starts at the input value attribute, and under some assumptions, it can't go past the label element. We'll talk about these assumptions a bit later. So we can ensnare this exploit by searching for this specific point in the document. So this is how our algorithm basically works. From the start of the document, we do a linear scan down to the first injection start point, which is the first HTML element before the injection. And similarly, from the document's end, we do a linear scan up until the injection endpoint, which is the next HTML element after the start. This essentially sandwiches the exploit so we can get rid of it effectively. Our signatures For our signatures, we know that injections must have a start point and an endpoint. They can't go on infinitely. And second, the dynamic content cannot rearrange itself without executing code. So if we can filter this malicious content before the code has a chance to run, then it cannot alter its own location in attempts to protect itself against our sanitization. Our main objective in this case is to identify the injection points in the HTML documents. And we believe that long term this can be maintained by CVE writers, for example, white hackers, penetration testers, etc. CVE writing is a very well maintained and very popular process, and we believe that if signatures are easy enough and they don't take too long to write, then CVE writers will be willing to write the signatures. For our signature language, we have a declarative spec, mainly because it's easier to use and also because it prevents attacks from arbitrary code in case the signature developer is malicious. Our signature language must have enough expressibility to cover a wide range of situations because we want to cover a wide variety of exploits. And currently it provides several static sanitization functions because different sanitization might apply to different cases. So let's look at an example signature. In this case, we're again looking at a signature to cover our example. So the sub URL is the admin site for the responsive cookie consent plugin page. The software running in this case is WordPress. The software details is the responsive cookie consent plugin. The version affected is 1.5. The type of the signature is a string because we're looking for a string in the HTML document. Type that, without going into much detail, is there's just one single injection point in this document. The sanitizer we're using in this case is a regex because we want to limit the input to two numerical digits. And the endpoints are as we saw before. It's the input element up to the value attribute and the label element after it. For our filtering process, what we do first is we load the signatures, and we want to apply the signatures for the correct page. We perform version identification to test the underlying software. And then finally, after this, we perform the injection point search to find the injections and detect them as foreign points. And finally, we perform sanitization according to the signatures. We implemented this as a Firefox 69.0 extension. This is because it's easy to deploy and adopt. We can just upload it to the Firefox database and the users can install it in one click. Extensions can run in a privileged execution environment, so malicious code cannot try to run before the extension to try to defend itself against our sanitization. It also has web application context, so in the case where additional filtering needs to be done while the application is running, the extension will have enough context to determine if anything has to be done. and it also has the ability to interpose to the network level and the web application level. This is important because if we can impose at the network level, then we can run our filtering process before the malicious code has a chance to execute. Our extension basically sanitizes incoming network data according to the signatures. And currently the signatures come pre-packaged. We don't have a model for database uploading and downloading. For our evaluation, we have three main research questions. First, is our approach applicable to a diverse set of sites and vulnerabilities? Second, how long does it take to write a signature? And third, what is the impact on the browser? So I won't go into detail on the second and third questions in this presentation. The paper goes into a detail about our studies on this, but the main takeaways from this is that it took less than 5 minutes to write most of our signatures. So we believe that the CV writers will be willing to adopt this. And second, there's less than 10% runtime overhead for most of the top popular sites, and in this case, most of the runtimes were under 1 second. So for our approach viability, we want to evaluate the applicability of XSnare to real-world vulnerabilities. So we analyzed 100 recent XSS CVEs and see if we can write signatures for them. We use WordPress as a study platform for several reasons. First, WordPress powers almost a third of the web. And plugins are very popular and the main cause of vulnerabilities. There's upwards of 2,000 CVEs right now for WordPress plugins. Plugin code is widely available, so we can see it for ourselves. And finally, we can install many different plugins and analyze the different CVEs with only one framework. So for each CVE, we set up a Docker container with a clean installation of WordPress 5.2 and the vulnerable plugin, if any. In many cases, the vulnerability happened in WordPress core. For our results, we ended up analyzing 76 CVEs across 40 affected pages. 24 of them we could not reproduce. Our plugins the plugins we studied averaged about 500,000 installations. We were able to write 71 signatures, which covered most of our affected CVEs. And for the signatures we did write, 12 of them led to some element rearrangement on the website, but it did not affect usability. And one did lead to functionality issues. There was one button which wasn't working when clicked. We additionally analyzed 5 non-WordPress CVEs, and we successfully signed all of them. For some of our limitations, generalizability, we only studied a small number of frameworks and a limited set of CVEs, although we did include a few other frameworks other than WordPress. Our current implementation is still a prototype. Functionality and performance are limited, although they are looking very good with 10%, with only 10% performance overhead in terms of runtime. False positives and false negatives we didn't really study, or we don't have a rigorous method to study this right now. Although for our studied sites, we noticed that there were no false positives. In terms of usability, we don't currently have a study of usability, well, either for users that want to download the extension and use it, and for developers that are willing to write signatures. And finally, we believe that we can adapt our approach to be able to protect against CSRF, which is another common type of web exploit, using a similar signature language, but we were not able to do this. So in conclusion, our main contributions are that this client-side approach gives users the power to defend themselves against XSS. XSnare provides a framework to emulate server-side patches on the client side. CVEs provide a stable maintenance environment for the signature database, and this approach applies to a majority of the studied websites. And finally, performance overhead does not deteriorate user experience. This is a link to our extension on the Firefox site. Thank you for your time.